Hello everyone and welcome. In this video, I'm going to prove a very important theorem. The theorem is a sequence is convergent if and only if it is a Cauchy sequence. Alright, so let's get started. Now, there's two sides of this story, okay? Two sides of this theorem. First, we need to prove that a convergent sequence is in fact Cauchy. That's the first thing that we want to prove because this is an if and only if case. And then the other way around as well. And then next we want to prove that a Cauchy sequence is in fact convergent. Now, I must say one thing. When I say a sequence, I'm talking about real sequences. Okay, that makes a difference. Why? We'll discuss that in a later video, but I'm talking about real sequences. Okay, all right, so these are the two things that we need to prove. Convergent implies Cauchy, Cauchy implies convergent sequence. However, I already proved that a convergent sequence is a Cauchy sequence. I did this in one of my previous videos. So go and check that video, and from that video you can get the proof for the first fact. So I'm not gonna do that in this video, okay? Rather, I will focus on proving that a Cauchy sequence is a convergent sequence, and it's a very tricky proof. Okay, it's an easy proof. There are little things that we must be very careful of. Okay, and there are several ways of proving this. Okay, someone can use Bolzano-Weierstrass theorem and prove it. I will give that version in a future video after I talked about the Bolzano-Weierstrass theorem. But in this video, I will give you a simple but somewhat tricky proof. So yeah, let's get started. Okay, to prove it, let's erase this mess. Okay, and what are we trying to accomplish here? So we want to prove that we have a Cauchy sequence, and we want to prove that it's in fact a convergent sequence. All right. Now, how do you prove that a sequence is convergent? Can you think of a way? Well, one obvious way is that if you know the limit explicitly, then you can prove that the sequence is convergent by some way. But here the disadvantage is that we don't know the limit. We are working with a general sequence, right? So let's say the sequence is S sub n, by the way. All right. That's the notation for a sequence. All right. So then how can we prove that a sequence is convergent? Well, we learned one method in one of my previous videos. The method is, here's the thing. If we can prove that the limit superior of the sequence is same as the limit inferior, then this means the sequence is convergent, and the other way works as well. So if a sequence is convergent, limit inf and limit superior is same, and if the limit superior and limit inferior are the same, then the sequence is convergent. So if we can prove this, then we are good. All right, okay, that's our goal. Now the next question is then, okay, how do we prove that two things are equal in math? Now, there's a very famous trick, okay? So, the trick is, if we can show two things. The two things are, if we can show here that the limit inferior is less than or equal to the limit superior, that's the first thing that we must show. And then on the other hand, if the limit inferior is greater than or equal to the limit superior, then this means if these two inequalities holds, this means these two things are the same. They are equal. Okay. All right. So that's what we are shooting for in this proof. Okay. Now I'm refining the facts here. Okay. Now, if we can show these two inequalities, then we are good. All right. Here's one more thing. Now, if you look at the two inequalities, inequality 1 is a natural fact. Now, think about supremum. Supremum means the upper bound. Infimum means the lower bound. Okay. So, well, I should be precise. Supremum means the least upper bound. Even though it's least, it's an upper bound, right? Infimum means the greatest lower bound. Even though it's the greatest, it's still a lower bound. So naturally, we can think that, the upper bound is usually going to be greater than lower bound. Or in the worst case scenario, they should be equal, right? I don't know whether it's the worst case or the best case scenario. But anyway, at least, for very least, the upper bound should be greater than or equal to the lower bound. So actually, the first fact We don't need to prove this. It's a natural fact. It's a known fact. So we can take it for granted. It's already done. Okay, it's a fact. So at the end of the day, all what we need to do is we want to prove the second inequality. We want to prove that limit inferior. If we can prove that limit inferior is greater than or equal to limit superior, then we are done with our proof. Okay, hopefully this makes sense. I tried to create an roadmap. I know I didn't even start the proof yet, but this is the roadmap. Okay, just a quick recap. Again, we want to show that Cauchy sequences are convergent. We know a sequence is convergent if the limit superior and the limit inferior are the same. If you want to show that they are the same, all you have to do is you have to prove these two inequalities. But we can avoid the first inequality because it's a fact that we know. So we just need to prove the second inequality. All right. So let's get started. Let's start proving that second inequality. Okay, so since we are dealing with Cauchy sequences, okay, we can start with the definition of a Cauchy sequence. So what's the definition of a Cauchy sequence? Well, here's the start of the proof officially, okay? Right, let epsilon be greater than 0, any epsilon greater than 0, and Sn is a Cauchy sequence. We know that for a fact, okay, Cauchy sequence. So because of that, there exists an uppercase n, which is a natural number, such that for all m and n greater than uppercase n implies this inequality. This inequality holds. Now this is from the definition of a Cauchy sequence. Alright, now let's draw a picture simultaneously, okay, because then it will be easier for us to follow. Now what does this mean? So let's say we have a sequence and we have this uppercase nth position, and this lowercase n and lowercase m will be two terms of the sequence that appears after the uppercase nth position. So this will be little m and this will be little n. Now without loss of generality, let's assume n is strictly greater than m. Okay, that's not gonna affect. You can work with other way around too, but it doesn't matter. All right, now what I'm going to do is I'm going to simplify this inequality little bit. Okay, so I can rewrite this inequality as s sub n minus s sub m is definitely less than epsilon, but it's greater than minus epsilon. So I drop the absolute value. Okay, right, now let's work with the right hand side. What I'm going to do is I'm going to move s sub m to the right hand side. So we get s sub n is strictly less than s sub m plus epsilon. Now this is an important fact. Let's say fact number 3. Now what does this mean? How can we read this mathematically? Now if you think carefully, okay, this means s sub m plus epsilon is an upper bound for s sub m. Do you agree? Yes, right? Okay, so what does this mean? Well, now we can say, so since s sub m plus epsilon is an upper bound for s sub n, we can say the supremum of s sub n that comes after uppercase nth position. Now this uppercase nth position, that plays an important role, okay, because it's like a condition. We are talking about the terms of the sequence in this region that comes after this uppercase nth position, so it's very important to have it here. Okay, now the supremum, okay, of s sub n in this region is then actually going to be less than or equal to s sub m plus epsilon. So let's digest this. I mean, think about this. S sub m is an upper bound, right? What is the meaning of supremum? Supremum means the lowest upper bound, right? So either the supremum is going to be equal to s sub m plus epsilon or less than s sub m plus epsilon. Okay, that's something that we can naturally write. Okay, so now what we are going to do is let's give a name to this supremum. Let's call this supremum as u sub uppercase n. Okay, I didn't use the letter s because we already used the letter s for sequence, so I didn't use the letter s for supremum. Okay, so supremum, let's think it as the second letter of supremum u. U is the supremum. U sub uppercase n. The uppercase n is again very important. Okay, right, now at this point we have this fact. Okay, what I'm gonna do now is that I am gonna move this epsilon to the left hand side, and I can say u sub n minus epsilon is less than or equal to s sub m. Okay, I rewrote this inequality 4. Okay, great. Now what does this mean? Think about this again. Now this means u sub n minus epsilon is a lower bound for s sub m. Do you agree? Yes, right? Okay, so since we are talking about lower bounds, let's talk about infimums now. Now, infimum is the greatest lower bound, right? So the infimum should be actually greater than or equal to u sub n minus epsilon, right? Infimum of s sub m. Now m greater than uppercase n. Now why s sub m here? Because we are talking about s sub m here. Okay, previously we talked about s sub n. So this here, it's the supremum of s sub n. Now here the infimum of s sub m. Try to understand that very carefully. Okay, those little things are very important when you're writing a proof to be accurate, especially if you're doing an exam or homework. Okay, right, I mean every time it's important, but it's extra important that you want to get those things right when you're doing an exam or homework. But anyway, so this is the fact. Okay, so then s sub m is definitely greater than this all. Okay, all right, now look at this. Now we have a, let's see, how do I put this? So we have a relationship between infimum and supremum. Remember, this uppercase u sub n is the supremum. So let's write that here. Okay, so uppercase u sub n is the supremum. So supremum of s sub n for the terms n greater than uppercase n minus epsilon is less than or equal to, let me find space, infimum of s sub m, where m strictly greater than n. Right, now we have a relationship between supremum and infimum. You know what I'm going to do? I'm going to move this epsilon to the right hand side. I know I have been moving this epsilon in all directions, right? Okay, so this is another statement, right? Now at the moment we only have supremums and infimums. Remember, in the goal of our proof, we want to work with limit infimum and limit supremum. So now what we want to do is we want to convert the supremums and infimum into limit superiors and limit inferiors. How can we do that? Now here's one tricky part that you need to digest. Okay, I will try to explain clearly as possible. Now I have talked about these things in one of my previous videos when I talked about limit superior and limit inferior. To understand the proof from here on, you need to have a very good understanding of limit superior and limit inferior. If you do not have that, please go to my limit superior and limit inferior video and watch that as well. But I'll try to make it accessible. Now, how do we get the limit superior out of this? Now, try to understand this. Okay, now here I am just taking the supremum of a one collection. Try to understand. What do I mean? A supremum of one set. That means the set is the s sub n comes after uppercase n. Okay, right. Now what I'm going to do is I am going to move, or I am going to let uppercase n goes to infinity. So I should write it here. So let uppercase n goes to infinity. That means I'm moving this uppercase n to the right hand side of this sequence. And then while you are doing that, I'm going to take the supremum each time. So try to understand this. Here's the part to digest. I will be taking the supremum of many sets. Okay, when we let n goes to infinity. So at the end of the day, I will get a collection of supremums. Okay, a set of supremums. All right. Now, if you take the limit of that set of supremums, that is the limit supremum. Okay. All right. So let me write it. So the limit supremum, you get the limit supremum by letting uppercase n goes to infinity. Okay, hopefully that makes sense. So limit supremum is actually the limit of bunch of supremums. Okay, all right, supremum collections. Right, now here's another part, hard part to digest. The thing is that limit supremum is actually smaller than or equal to the supremum. Now how come this happens? Here's the thing. Now, if you think about this collection of supremums, it's going to be a decreasing sequence. Okay, because you get a collection of supremums. This collection of supremums is going to be a decreasing sequence, or they are, or they will be the same value. Okay, I discussed this in the video where I teach limit supremum and limit infimum. Okay, if that doesn't make sense, just write a sequence, write any random sequence, decreasing or increasing sequence, and chop the sequence each time by starting from the first value and get a collection of supremums, and see that collection of supremum is either going to be one fixed number, or it's going to be a decreasing sequence. So when you take the limit of a decreasing sequence, you can find the limit in the very bottom, right? So that's why the limit supremum will be smaller than the supremum. Okay, all right, now this is less than or equal to, remember we have the infimum here from here. Okay, so infimum, I need more space, s sub m greater than n plus epsilon. Okay, not C, epsilon. All right, so one more step to go. Okay, we are almost done. Now let's talk about the limit infimum. Now we have the infimum, right? Now again what we do is, when n goes to infinity, we are taking the infimum of bunch of sets. So then what we get is collection of infimums. Okay, a set of infimums. Now here's the cool thing. Now this set of infimums, the limit of that set of infimums, we call it the limit infimum. Okay, and the cool thing is, the limit infimum will be greater than the infimum, greater than or equal. So infimum of s sub m greater than n, and we have this plus epsilon. Okay, we have to write that plus epsilon here. So basically what I'm saying here is, infimum is smaller than or equal to limit infimum. Now here's the thing. Just like in supremum, so I said the collection of supremum is a decreasing sequence. That's why the limit is on the bottom. So that's why the limit superior is smaller than the actual superior. Okay, supremum. Now in the case of infimums, the collection of infimum is going to be an increasing sequence, or it's going to stay fixed. Now if you find the limit of an increasing sequence, it's going to be on the top. Okay, so the limit infimum is going to be greater than the infimum, okay, or equal if it stay fixed. Okay, right, that's the idea. So that will make sense if you have a good understanding of limit superior and limit inferior. Okay, I cover all these things in my previous video where I talked about limit superior and limit inferior. Okay, anyway, now what we all want is this limit superior and limit inferior part. So let's drop whatever in the middle. So my final statement is going to be, so let me try to write this very clearly. Okay, my final statement is, limit superior is on the very bottom, as you can see, n greater than uppercase n, and we can see the limit inferior is on the very top, s sub m greater than n, strictly greater than plus epsilon. Right, now still there are two problems. One problem is, here you have s sub n, now you have s sub m, and the other problem is, we have this plus epsilon. We have to get rid of plus epsilon, but we will get rid of that at the end of this proof. Okay, how can we make sure that we have s sub n and s sub n in both places? Okay, so we have s sub n in one place and s sub m in other place. Now here's the thing, here's another hard part to digest. Okay, all right, again this boils down to the understanding of limit superior and limit inferior. Now in the very beginning of the proof, remember I said, without loss of any generality, n is strictly greater than m. Now because of that, I can say, now limit here, limit superior. Okay, let's, rather than writing that n goes to infinity, let me write limit superior. Limit superior s sub n, I can write like that, is now strictly less than, not strictly, less than or equal to limit inferior s sub m plus epsilon, and limit inferior of s sub n is greater than limit inferior of s sub m. Okay, now this is the new statement that I wrote. Okay, so what I'm saying again here, limit inferior of S sub n is greater than limit inferior of S sub m. How come that happened? It happened because of this statement. Now let's go back to picture. Okay, right. How can we understand this from a picture? Now you are calculating the infimum, right? Now when n is greater than m, okay, the set is smaller, right? The S sub n set is smaller than S sub m, right? S sub m set is larger, right? Because n is larger than m, okay, the set containing S sub n will be small, right? So smaller the set, the larger the infimum is going to, limit infimum going to be. Okay, if you don't believe me, again write a real example of a sequence and test, and I discussed this again in my previous limit superior and limit inferior videos. That's the reason why we can write this statement, okay, where limit inferior of S sub n is greater than limit inferior of S sub n. So those little things are very important, okay, that's why I am explaining everything. So at the end we can say, all right, let me again try to write this clearly as possible. So limit superior is now less than or equal to limit inferior S sub n plus not C epsilon. All right, now we have one more step to go, which is easy. Trust me, we have to drop this epsilon. How can we drop this epsilon? Well, remember, this works for any epsilon. That's how we start the proof, right? Because this Cauchy definition of Cauchy, let epsilon greater than 0. That means any epsilon, okay? So since this is valid for any epsilon, we can drop that epsilon and we can say this fact: limit superior is less than or equal to limit inferior. Now, why we can drop that epsilon? Again, now if you don't believe me, write an example. Think about this. 5 is less than 7 plus epsilon. This is valid for any epsilon, right? Any epsilon greater than 0. Okay? Valid for any epsilon greater than 0, right? So we can say 5 less than 7 by dropping epsilon. But the important line here, important statement here is that this statement should be valid for any epsilon greater than 0. Now, for example, think about this. 5 is strictly less than 2 plus epsilon. Does this valid for any epsilon? No, right? This doesn't valid for epsilon equal to 1. So that's why we cannot write 5 less than 2. Okay, right, it has to valid for any epsilon, then we can write this. So based on that, we can write this statement, which is exactly what we wanted. Okay, and the other way around is, the natural thing is that the limit supremum is naturally greater than or equal to limit infimum. Okay, this is the natural fact which you don't have to prove. So because of these two things, we can say limit supremum of the sequence is same as limit infimum, hence the sequence is convergent. So that's the end of the proof. Okay, so it's a small proof, but it's very tricky, and there's a lot of little details hidden inside the proof. Okay, so this is a longer video, but I tried to explain everything, and hopefully it makes sense, and I will hopefully catch you in the future videos of real analysis as well. So thank you very much.